Okay, welcome to the last talk this afternoon. And our speaker is Sakura Schafer-Nameki from the University of Oxford. And she'll talk about 5D superconformal field theories, flavors, and BPS states.
Okay, thank you very much. Thanks, first of all, to the organizers for setting up this wonderful meeting. And it's a great pleasure to talk about this topic here that I'm very excited about. It's about five-dimensional superconformal field theories. And it's work in collaboration with four postdocs, Fabio Pruzzi, Yinan Wang from Oxford, and Craig Laurie and Ling Lin from UPenn. Sort of the short appetizer paper appeared last week, and there'll be two longer, less sort of just digestive things, more sort of longer digestive things appearing very soon with more details on the background geometry and the field theory. I have to say one thing, I have a cold, so I might not be so easily audible, and I'll be having a cough candy in here as well, so I apologize for this, otherwise I'll be coughing and you won't hear anything. Okay, so why five-dimensional n=1 gauge theories and superconformal field theories? So first of all, what are these things? So n=1 SCFTs in five-dimensional are intrinsically non-perturbative objects. In some instances, they have a low-energy effective description in terms of a gauge theory, a weakly coupled gauge theory. In n=1 supersymmetry language, there are two important multiplets, the vector multiplet and the hypermultiplets, and some representation of the gauge cube. And the parameter space that will be of interest for us is parameterized by vacuum expectation values of the scalar in this vector multiplet, and that parameterizes the Coulomb branch. So when you get lost in this talk, you should always go back to the classic examples of these theories, which were developed in the 90s, I believe, by Nati, and then later with Dave and Nati in a follow-up paper, which are SU2 gauge theories with NF fundamental flavors. The Coulomb branch is one-dimensional, obviously, so I will refer to these theories as rank 1 theories. And the weakly coupled flavor symmetry is an SO2NF, and it is understood to be enhanced in the strong couplings in the UV to the exceptional groups E sub NF plus 1. So in general, if you look at a 5D SCFT, it's quite difficult to extract what the properties of this UV fixed point are. In particular, these sort of enhancements of flavor symmetries are usually studied case by case. Okay. So what is the motivation for revisiting this in this day and age? Well, one motivation is recently 61,0 theories were classified. So in terms of F theory on elliptic Calabi-Yau threefolds. There's a close relationship between 6D and 5D theories. I can just put the 6D theory on a circle. That gives not a 5D SCFT per se, it actually gives what I'll refer to as the 5D marginal theory. That theory itself actually UV completes in 6D. But I can mass deform this marginal theory, and then it starts flowing to other theories in 5 dimensions, which gives rise to 5D UV fixed points, or superconformal field theories. So one question that you can ask, given the 6D classification, is can we identify all 5D theories that can be reached by circle compactification plus mass deformation in our G-flow systematically in some sort of nice framework. The question whether these are all 5D theories is sort of a slightly more complicated question and hinges really on the classification of canonical singularities in Calabi-Yau threefolds. So whether these are actually all descending from such geometries as sort of conjectured in Shi and Yao's work. Okay, so the proposal that we put forward, and I'll explain how it relates to other works in a moment, is we'll construct 5D SCFTs from M theory on elliptic Calabi-Yau threefolds, but there's a catch, which is with non-flat fibers. And I'll explain to you what that means and why this is a useful tool to have in this description. We'll describe the extended Coulomb branch. So this is both the scalar vest, but also additional Coulomb branch parameters which correspond to weakly gauging the flavor symmetry, the classical flavor symmetry in 5 dimensions. And the upshot of all this will be an extremely succinct graphical description in something that we coined combined fiber diagram, or short CFD, which actually will characterize 5D SCFTs. So one of these diagrams will be one-to-one to our CFT. What is this diagram going to encode? It'll encode the strongly coupled flavor symmetry. So in these Seiberg theories, it'll be this ENF+1. Manifestly, it'll tell you about the mass deformation, so it'll tell you about how you flow from a given theory to other theories. So descendant SCFTs. And also we can extract some aspect of the BPS states. So that's a very nice thing, and it just fits into a nice graphical description. So that'll be the goal of this talk. Okay, so the general strategy will be, as I said, starting in 60. There's, say, some 61,0 SCFT. It has some flavor symmetry. We can put this theory on a circle that gives the marginal theory. We turn on masses for flavors, and it gives, say, a weakly coupled gauge description in many cases with a gauge group and a classical flavor symmetry, and then we let that theory flow, and that gives the UV fixed point. Alternatively, you could also start with the 60 theory, go on to the tensor branch of that theory, and then put that on a circle. So what we'll follow is actually more the field theory analog of this, but put into sort of geometric framework. Geometrically, what this means, and I'll explain this in more detail, is we'll consider, so the 60 theory is some F theory on elliptic Calabi-Yau threefold. It has a particular singularity, which makes sure that there is a superconformal theory sitting there. So it has some flavor symmetry. The simplest cases, there'll be a G1 times G2 flavor symmetry. Putting this on a circle means we look at the M theory compactification on a singular Calabi-Yau threefold, the same Calabi-Yau threefold as in the F theory. And then going to basically a gauge theory description means you do a non-flat fiber resolution. So this non-flat fiber resolution will introduce compact cycles into this geometry, and then the analog of the RG flow to the UV will be then a partial singularization of these geometries back to shrinking some of these cycles. So there's of course been a lot of work recently on this sort of topic as well, so I need to explain what is new here. There's earlier developments, and this, of course, is a very, very partial sublist. Recent different approaches, in particular, I think one that I should highlight that's very closely related is this paper by Jefferson, Katz, Kim, and Waffa. Again, looks at M theory on Calabi-Yau threefolds. Their strategies, however, more following this tensor branch analogy, where you first take this elliptic Calabi-Yau threefold, you blow up the base, and then you go to the M theory side. This has sort of, the approach is equivalent mathematically to what we'll be doing. However, they're not actually retaining the structure of these elliptic vibrations in their geometric operations. In particular, when you pass from a given CFT to another, you have to do a flop transition, and those don't necessarily retain the elliptic vibration structure. So what we'll try to do is actually keep that through, and that's actually what will encode the flavor symmetry of the CFT. So the new idea is to really use these non-flat resolutions to keep tracking the flavor symmetries throughout the RG flow chain. Okay, so let's actually write down what kind of geometries we're looking at here. So I have to do a little bit of F theory after all. So 60 SCFTs from F theory on Calabi-Yau 3. Well, F theory, we need elliptic vibration. It's elliptic Calabi-Yau threefold, so there's a base, it's a twofold. For our purposes, because we're only interested in CFTs, we're not interested in coupling this to gravity, the base is non-compact. Think of it as C2 with some local coordinates, U and V. And we will assume that this has a section, so that's an elliptic curve sitting at every point, and so we can put it into some Weierstrass form. So if this Weierstrass equation and there's a vibration over the base, The interesting loci are, of course, where this vibration becomes singular, so some of these torus cycles pinch. And that's characterized when the discriminant of this Weierstrass equation vanishes. So, say, take this local coordinate u equals to 0, and if delta has a vanishing order along u equals to 0, you assume then that there is some singularity above it. And in fact, Kodaira classified what type of singularities these are. So in fact, in codimension 1, so in complex codimension 1 in the base, the fibers that are possible over these loci are one-to-one with essentially decorated affine thinking diagrams, up to some small exceptions. So, for example, here is some AN-type diagram. This is some exceptional diagrams here, and then there's somewhere also the 0 stars. Well, they're here. So the D-types. So in codimension 1, there's a classic story, and in fact, given a Weierstrass equation, the vanishing orders of F, G, and delta tell you exactly in which case you are, what type of Kodaira fiber there is, and what sort of symmetry you have, some AN, DN, or some E type. So I highlighted here at the bottom this case when F, G, and delta vanish to order 4, 6, 12, or higher, and those are the loci where the fiber becomes non-minimal. And in codimension 1, we will exclude these things. But it's interesting to now look at this in codimension 2, where we'll start including such singularities. So in codimension 2, when we have collisions of two of these singularities, so u equals to v equals to 0, say, is that locus, there's the option to have a minimal singularity or a non-minimal singularity. So minimal means the enhancement still fits into this table here. So you get effectively, again, a collection of rational curves intersecting in some generalized Kodaira fiber. What's important is this resolution of the singularity in this case, discrepant resolution, is still complex one-dimensional. The fiber remains complex one-dimensional. In the non-minimal case, so if at this locus u equals to v equals to 0, fg delta vanish to 4, 6, 12 or higher, there are two ways out. So either you say, well, let's just remove this locus u equals to v equals to 0, so we blow up the base. Or you say, well, let's just keep blowing up and see what happens to the fiber. And this is where we'll see these non-flat fibers. And contrary to this minimal case, the fibers now will actually have higher dimensional components. So let's just recap briefly what this first case is, where we blow up the base. This is what standardly is done in the 60 literature in F-theory. So say you have a u equals to v equals to 0 non-minimal singularity. It should be blowing up, not blowing up, a P1. So you can actually remove this point and insert a P1 with self-intersection -1. So say if there are two such components, say curves with self-intersection numbers n1 and n2 inside the base, and there's a non-minimal locus where they intersect, then we can replace that point by a curve. And if that's still non-minimal, this fiber above it, we can keep doing this. So one example of this sort of story is if I have two singularities collide and give a non-minimal singularity. The simplest, sort of exceptional case is E6, E6. The Weierstrass model takes this simple form. This is just the E6 singularity along U and V, and the mean at U equals to V equals to 0. And now blowing up this point repeatedly until we get a minimal vibration gives this sort of model where there's a non-compact E6 on one side, there's a -1 curve, -3 self-intersection number curve, -1 curve, another E6 non-compact curve, and on top of this -3 there's an SU3. So this is what the so-called E6, E6 minimal conformal matter theory. That's one example of a 61,0 theory. That actually we'll look at later. Okay, so this was what you do in 6 dimensions, where you actually have, you blow up the base, you go into the tensor branch. What you want to do is, we actually blow up the fiber. So what happens if you have a non-minimal locus in codimension 2, and you blow up the fiber? So what happens is that say we start with an E8 singularity along u equals to 0. So we do the standard resolutions. We see the affine E8 Dinkin diagram in terms of -2 curves appearing. We collided with an I1. And at the intersection point, the vanishing orders are precisely such that we get a non-minimal singularity. So if I now do the resolution, in fact, I get some splitting of these P1. So in this case, there's one of these simple roots of D8 curves associated with the simple roots, splits into two P1s. But the key thing is that there's now a surface component appearing above this point. And you'll say, okay, so now the fiber seems to not be one-dimensional anymore, right? So this is what is meant by non-flat resolution. If your entire geometry otherwise was completely non-compact, so the base is just C2 essentially, when you're doing these resolutions, then this surface component, in fact, is the only compact surface now in this geometry. So if we actually put this into a context of M-theory compactifications, this surface here is sort of the only compact surface, and that's the only one that can actually give rise to a U1 gauge field in an M-theory context. All these other symmetry groups that are fibered basically over the non-compact curves U and V equals to 0, those are actually flavor symmetries. So the rule, how we'll read off the flavor symmetries of the 5D theories, will in fact come from what collection of P1s from the codimension 1 fibers are actually contained within the surfaces that we obtain from this non-flat resolution. Yeah? Sorry? So you're asking in terms of BPS states. I will discuss BPS states almost at the end. And I can tell you in this specific case, in fact, what the spin 0 BPS states are. So, sure. Modulo issues such as, Sheldon Katz is the expert in this, right? So, yeah, sure, you can, in fact, study indeed BPS states for these 5D theories by looking at the curves in these non-flat fibers. Good. So let's actually recap some basic dictionary between M-theory and Calabi-Yau and 5D gauge theories or CFTs. This goes back to interrogator Morrison-Seiberg. The only new insight is we want to think of these compact devices as exactly coming from these non-flat fiber components. Okay, so that's the extra input, and this somehow lets us pass through this whole framework in a quite systematic way. But let's recap what sort of the rules of the game are. We put M-theory on non-compact Calabi-Yau 3. As I said, compact devices will furnish the U1 gauge bosons. If these surfaces have some rulings, so I can collapse them to some curves, I'll get a set of singularities of curves. The U1 symmetries can enhance to some non-abelian gauge group, and there can be multiple such rulings for given geometry. If I can collapse the surface to a point, this means I'm going to a strong coupling limit. The Coulomb branch, basically, once I include a matter in some representation RF of the classical 5D flavor symmetry, is known to have this one loop correction, this prepotential from these matter fields. So, in fact, what really we should be looking at, on what the geometry actually describes, is an extended Kähler cone, which includes both these Coulomb branch parameters, but also mass deformations, which allow us to give masses to these hypermultiplets that transform on the flavor symmetry. The strongly coupled flavor symmetry is determined by the curves of the ADE singularity that are contained in these compact surfaces. So this is just in this case here, you see that these E7 worth curves contained in the surface S in this particular resolution. So in fact, in that case, we will expect an enhancement to E7. And usually this flavor symmetry is enhanced compared to this classical one. And then finally, this is this comment regarding your question, right? You can look at M2 branes wrapping curves, and this will give rise to BPS states. Okay, so let's do an example. And let's go back to these rank 1 theories, and let's see how we get from these non-flat resolutions this sort of class of theories that are well known. So the starting point is the E string. The E string is basically constructed from the collision of E8 with I1. So just like in this cartoon I showed you earlier, we can write down the Weierstrass model, or what's slightly nicer, the so-called Tate model. The vanishing orders for the E8 singularity are these in this equation here, and the I1 just has 0,0,0,1. So you see here there's U's along here, and then there's this one coordinate V appearing here. And as I go to U equals to V equals to 0, the singularity becomes non-minimal. And so now we can do the resolution. So we first resolve the codimension 1 singularity, that's this 2-star fiber. We get non-compact devices that are rational curves fibered over this locus U equals to 0. They intersect in the affine-Dynkin diagram of E8. And then there's one more resolution, which is exactly this non-flat fiber resolution, and that will furnish the Cartan of the gauge group. And so now different resolutions will contain will make different P1s be contained inside the surface, and those will precisely then correspond to different strongly coupled flavor symmetries. So different resolutions in particular we can think of being related by flop transitions. So you can either do different blow-ups every time and see what kind of curves are contained in S, but you can also just start with, say, one where everything is contained in the surface and then do flops and flop out the curves from the surface. So the strategy will be start with the marginal theory. So the marginal theory has all the rational curves of the E8, the affine E8 contained in the surface, and then do flops. So that blow up will give rise to a surface that has the geometry of GDP9, and so we can now basically, this is sort of the collection of curves, basically all the P1s that are contained inside this surface. And it's of course very ugly, but in the end, all we actually will need to know is what are the self-intersection numbers of these curves in the surface. So since this is the last talk, and I don't want to bore you with more blow-ups of some horrendous elliptic vibrations, you will just simplify the picture and say, let's just look at this diagram here. So these were just these curves that I showed you before, with numbers -2 and colorings green for those that had self-intersection number -2, and then there was 1 -1 curve. So this is the fiber for the marginal theory. So it's just the E string on a circle, and now we actually want to start doing flops. And basically the curve we can start flopping on is this -1 curve. So instead of now running through the very classic algebraic geometry of how we flop curves, I will just define for you a way of just formalizing this in terms of these graphs. So basically, we'll start with a diagram that represents these curves, and then all the curves that I'm drawing are contained in these non-flat surfaces. Generically, we'll have a collection of surfaces, so we have a reducible surface. Given the rank, there'll be a rank many surface components. And then I'll define a diagram, which is this combined diagram, a combined fiber diagram, which has vertices given by the curves. They're labeled by their self-intersection number. The edges are basically, Ci, Cj is the number of edges between the two vertices. And then we'll mark some vertices, those which have self-intersection number -2, and those will be colored, and in fact those will give the subgraph, that'll be the Dynkin diagram of the supercontrolled flavor symmetry. So this is basically just putting into some more formal framework what this reduced fiber looks like in the rank 1 E string. And I also want to define what now these flop transitions are. So given one of these diagrams, there'll be descendant diagrams that are obtained by removing a -1 vertex and then updating all the numbers in the following way. And this is just doing a flop on this -1 curve. And in this way, we'll get a whole network. So starting with one of these CFDs, or CFTs if you want, we can get a whole sort of tree of theories descending from that. Okay, so these transitions in the geometry I said are just flops. So collapses of -1 curves. So these rules are just sort of encoding that. And from the physics point of view, you start with a 5D CFT, you give masses to some of the flavors, and then you let the theory run, and it triggers this RG flow to another CFT. And you can keep going, and by doing this, you basically get the whole network. Okay, so let's apply this rule. So this was the marginal theory for the E string. So there is 1 minus 1 curve. So I basically have no choice. I just start there. It says I remove this curve and then I update the next one to minus 1. And in fact, I didn't mention this, but whenever a vertex, a minus 2 vertex, changes self-intersection number, I uncolor it. Okay? So the first step will give us this. And of course, here the sub-diagram is now Dynkin diagram E8. So as per this rule earlier, this will basically give rise to the flavor symmetry of the theory obtained by doing the first master formation of the marginal theory. Then we can continue. There's still no choice. E6, E7, SO10, SO5, SU3 times SU2. And then in this point here, we have now 2 minus 1 curve. So there are now 2 options to do the graph transition. Either we go to this SU2 theory, or we go on this side here, and there's still a minus 1 here, and we get this diagram. So putting all this together, we now get exactly this chain of sort of theories. So you have the SU2 with 8 flavors, that's the marginal theory, and then we get the whole range of theories, including these 2 theories that SU2 with theta angle 0 and pi, as well as the theory at the very bottom that doesn't actually have a weakly coupled gauge theory description. Okay, so this is, you might say, well, okay, so that's nice. This is sort of deleting nodes on Dynkin diagrams, right? To read off now the flavor symmetry from these green nodes. But can you do more? I mean, this is rank 1. What about rank 2 theories? And luckily, recently, the rank 2 theories were classified geometrically in this paper here, and then from PQ5 brain webs by this group here. I think Kim Yong-lee is somewhere here in the audience too. Anyway, so there's also a network of theories that is known, and there's some weakly coupled gauge theory descriptions for these. So our strategy will be to run the same sort of algorithm. So apply this find the sort of marginal CFDs for rank 2 theories, as well as then apply the CFD transitions, and in this way map out all the theories in rank 2. So before that, I just want to give you a flavor of what these non-flat resolutions actually look like, right? So these CFDs, we're just keeping track of what kind of curves were actually contained in the non-flat fibers. In rank 2, there's one marginal theory, which is the rank 2 E string. So that's just E8 collided with an I2 singularity. And you can ask, so what sort of new features do you get when you look at these non-flat resolutions? So this is what I'm showing here is the E8, the codimension 2 fiber, so just the rational curves, and the colorings tell you whether they're contained in one surface or another surface. We have 2 surfaces because it's a rank 2 theory. So in this first example here, these splittings here are basically saying the curves of the E8 Dynkin diagram split into, there's one root alpha 1 that's split into 2 curves in codimension 2, and the same here and here. In this case, there's a curve that splits into 3. So depending on what resolutions you do, you get these sort of different fibers. The thing to note here is that in this case here, there's a full, so if you combine all the minus 2 curves that are contained in the fiber, so there's this root here and this root, this is an SU6. There's an extra U1, which I'm happy to explain offline. So in this case here, we get an SU6 flavor symmetry. There's a different resolution where essentially everything except for this curve here is contained. This orange stuff contains everything. And the other surface contains only one curve. This also has SU6 times U1. And in fact, these 2 resolutions will just correspond to different gauge theory phases that flow to the same CFT. So there are all kinds of equivalences in these non-flat resolutions that we need to mod out to actually get the actual distinct CFTs, and these combined fiber diagrams are exactly engineered to do so. And so here is another example which gives you SO12 times U1. But anyway, so the point is don't do these non-flat resolutions, find the marginal CFDs, so the CFD diagrams associated to the marginal theories coming from 60, and then apply the CFD transitions. So in rank 2, there's, as I said, the rank 2 E string. The CFD at the top here looks like this. So there's this affine E diagram, there's the I2 fiber, and then the 2 -1 curves that connect them. So for this, to obtain this diagram, you actually do have to do the resolution, but from there on you just sort of descend algorithmically. There's another theory that is a starting point in rank 2, which is the D5-D5 conformal matter. So that's two isotents colliding. There the marginal CFD looks like this. So this is just the D10 affine Dinkin diagram with 2 -1 curves at the end, and then there are these two others starting points which look like this. These are sort of quotient identifications of some simply laced diagrams. Okay, so this is now, if I start with the D10 diagram, I was hoping there's a huge lecture theatre and one big screen so I can finally see these show this. So you might not see it in details, but there's this starting diagram, and basically, let's go back and look at, so this is this diagram here. Up to graph equivalence, there's just one way of starting the RG flows. So say we pick this one here, and then we descend. Actually, this is the first theory, and then we can have these two options, and this generates this whole tree of descendant theories. The coloring is basically saying if the theory appears both from this D5-D5 conformal matter and the rank 2 E string, it's colored in green. The Chern-Simons levels here refer to the SU3 gauge theory realization. The pink theories have SU2 times SU2, so these are these theories here, SU2 times SU2 gauge theory realizations, and these four gray theories are actually without any weakly coupled gauge theory realization. So this is the class of descendants from the D5-D5 conformal matter. From the rank 2 E string, we again do the same sort of tree, same rule. Here, these ones are generated only from this rank 2 E string. The green ones are overlapping with the D5-D5 conformal matter, and the gray ones are again without any weakly coupled gauge theory description. Okay, so, and then there is other curious ones. We repeat the same thing, and in the end, the nice thing is from these, in fact, we get the complete agreement with these works by Jefferson et al. And by Hayashi et al. From completely different methods, and essentially not doing any kind of geometric operations, simply applying sort of these CFD transition rules. Okay, so what actually how can we back this up? First of all, there are explicit geometric resolutions for these cases. So this is not just sort of doing some graph operations. We actually do check that this agrees to some non-flat resolution in each case. There's also a gauge theoretic cross-check. You can map out the Coulomb branch for these theories and sort of match at least those theories that do have a weakly coupled flavor, weakly coupled gauge theory description. In this case, SU3, SP2, or SU2 times SU2. Okay, so let me now comment on the BPS states. The BPS states arise from wrapped M2 branes. And so we'll look at only genus equal to 0 states. And in fact, they transform under the massive little group in 5 dimensions in this representation Rn, where n is the dimension of the moduli space at MC. So this is computing basic Gopa-Kumabaffa invariants in these geometries. And so from these CFDs, we essentially are furnished with a collection of curves, and we just now want to know what are the M2 brane wrapped states and what representations under the strongly coupled flavor symmetry do they transform in. And so, for example, for the rank 1 theories, right, so these were these theories that I listed earlier. These were the flavor symmetries, the gauge serialization, the spin 0 states are computed like this, and this is an agreement with the earlier results by Clem, Huang, and Poreczki. And I think this can be extended by something we're looking at the moment. So you can ask, well, so you've check things that are known? Can you also do things that are not known? So yes, sure. So what about higher rank theories? So one simple extension is to look at the decay minimal conformal matter theories. So you have, as before, I showed you already the D5 case, but now this is just a D2K affine Dynkin diagram with -2 curves and then 2 -1 curves attached. That's the marginal CFD for these theories. Such theories have weakly coupled gauge theory descriptions as follows. So either in terms of SU-type gauge groups or quivers, SU2 quivers with 4 flavors on each side, or as SP gauge groups. And so this already appeared in the rank 2 case. And so one question is now, what are the descendant theories from this? So we already saw this in the case of the rank 2 series, but so this is now even smaller. Okay. Anyway, so what actually this list here is, or maybe I can undo this full screen mode and just show you a zoomed version of this. No. Okay. So let's at least look at this sort of example here. So the starting configuration is this marginal diagram. We apply these CFD rules to descend, flopping this curve here to this theory here. This has SO4K flavor symmetry, and this is sort of BPS states at spin 0. At the bottom, we're listing the weakly coupled gauge theory descriptions and so on. And when these are connected, then so every graph transition corresponds to some RG flow between these theories. So this maps out a full diagram of such theories. And how do I go back to the full screen mode? No. These are feeling a little less scaly. Thank you very much. Okay. So we then realized that in fact, okay, so for a decay, there are K -2 squared -3 descendant CFTs. 2K -6 of these don't have any weakly coupled description in terms of a gauge theory. If you look at this subclass of theories which have a gauge theory description with this gauge group and M flavors, then in fact they have SCFT flavor symmetries enhancement given in this table here. So this is just read off from this big table here. So these are arbitrary rank theories. And then we realized in fact that only last year Hanani, using completely different methods, had exactly computed these using his magnetic quiver description. And so this actually was a surprising coincidence that actually we were precisely deriving these things from basically just looking at the simplest next extension. Okay, so this is sort of very reassuring. There are some, of course, also interesting other theories that sort of go beyond looking at things that people have considered. So E66 conformal matter, that was a theory I mentioned early on. So this is a collision of two E6 singularities. In 6 dimensions, you first blow up the base onto the tensor branch, and you see this actually has this SU3 gauge node with -3, -1, -1, and 2 E6 flavor symmetries. This conformal matter theory has a marginal CFD given in terms of these two affine E6 diagrams connected by -1 curves. So this again doing one blow up and seeing that this is sort of the starting point fiber diagram we need. And now we can run basically an algorithm to look at all the descendants starting with this theory. There are 207 descendants CFTs. Up to, so of course, we want to not overcount these, so all the graph equivalences are taken out here. So one question is, can you actually match this to something, doing some weakly coupled, some quiver, or some other gauge theory calculation? So there's one known construction and already appeared in the conformal matter paper, that this theory is conjectured to have the quiver description, essentially in terms of the 8 affine diagram with SU3 to 1 sort of gauge nodes. If you look at sort of what type of theories we can get from this description, there are still, in fact, 195 theories in this class that are sort of unaccounted for. And clearly some of these won't have a nice gauge description. They'll be just strongly coupled theories. But it will be very interesting to see whether there's some alternative gauge theory or quiver description for such theories. Okay, and of course we can extend this to any other conformal matter theory. So you can collide EH with, or EN with EK and do a similar process. And so using these rules, right, that I sort of outlined to you, we generate these descendant CFTs. Okay, so what actually have we learned? So one thing that we have learned is that fiber is good for you. Now scientists may know why, because they add flavor, at least to 5D SCFTs. Okay, anyway, so let me summarize slightly. So let me just give you sort of a brief summary. If you're given a 60 SCFT, and essentially in terms of some Calabi-Yau threefold in F theory, this seems to now provide a systematic way of exploring all the descendant 5D SCFTs. At least it's sort of the simplest instance that we can have now completely automatize is when you have two colliding singularities that are Kodaira type that collide in a non-minimal singularity. And I think that can also be applied to the higher rank E strings, to the higher the non-minimal conformal matter theories. So each CFT, SCFT, let's say, is characterized by one of these CFD diagrams, and they manifestly encode the superconformal flavor symmetry. All the RG flows that basically can be all the master formations, you can start from these, and also at least these spin zero BPS states. So this is the data that's manifestly encoded in these diagrams. And it also tells you then what is sort of the complete tree, starting with one marginal theory, what is the RG flow tree that descends to all the lower or descendant CFTs. So whether this provides a classification of 5D CFTs is really sort of a separate question, as I said at the beginning. That assumes that you actually can get all these theories from 6 dimensions by reduction. But if that is the case, then this certainly gives a very efficient way of sort of mapping out all these theories. Okay, so thank you very much. One more thing. So I want to make some advertisement as well. We are organizing a conference in Oxford in September called Geometry and Strings. To some of you, that's known as Geometry and Physics of F theory. We slightly wanted to expand the scope of the conference series, and we all got together and decided we wanted to include all of geometry. So that'll happen this September, and hope you can join us there. Okay, so are there any questions?
Any questions?
No questions.
No.
Okay.
So when we compactify 6-dimensional theory on S1, sometimes the 5D theory is superconformal, but sometimes it is not superconformal. There is some weakly coupled gauge fields. So can you distinguish these cases by your method?
So you mean you just put it on a circle. So this circle reduction is always just this marginal theory, right? So let's actually stick with this example. So this theory, so actually there's not a marginal theory. So these are the marginal theories, or in the rank 1 case, this one is the marginal theory. So that's just a 60 theory on a circle. Usually you would formulate it theoretically, you have a circle reduction plus some holonomies in the flavor direction, right? So this is basically turning on mass deformations. So that's exactly what I was describing here. So you are asking me whether I can see whether there's a weakly coupled gauge theory description, and the answer is yes. Whenever these non-flat fiber components have rulings, I can write the surface as a fibration, say with P1s. I can collapse this fiber to a curve of singularities, then I have a weakly coupled gauge theory description, right? So I keep the gauge coupling still sort of small, because the total volume of the surface is not zero, right? I just collapsed it to a curve. That's the weakly coupled gauge theory description. So if that exists, right, and that's a geometric question, then you have a weakly coupled description. There's one case here, which is this, where the geometry is a P2, the surface is a P2, you don't have a ruling, and so actually all you can do is you shrink the P2 to a point, so you cannot do some intermediate sort of collapse to a curve and then to a point. So in this case, you don't have a weakly coupled gauge theory description. In the rank 2 theories, this was, for example, these theories here, they don't have a gauge theory description either, these gray theories. Does this answer your question?
Any further questions then? If not, let's just thank Sakura again.
Okay.